Okay, our discussion today will be from section 11.5, geometric series and mathematical induction. But I will do these both separately, so let's start with the geometric series. Knowing that we spent last section talking about what a geometric sequence is, we should be all set to take that geometric sequence now that we can identify the terms, etc., and add it together as what we called the sum of those terms, and that sum of those terms is nothing more than our series. So looking at our first set of notes we need, remember our geometric sequence. That's over there on the left, and when we see the geometric sequence listed here for finding any term in our sequence, we now want to be able to add them, and there's our definition. A geometric series is the indicated sum of the terms of the geometric sequence. So if we could just generate the terms, add them together, we would have the series. But as you saw in your book, there is basically a formula for finding that series or sum in a shortened way. And you see that listed here. The sum of the first n terms of a geometric sequence is nothing more than s sub n equals t sub 1 times, in parentheses, 1 minus r to the power of n divided by 1 minus r. Now remember, looking at this as mathematicians, we can see that they have that restriction statement down here, r cannot equal 1, but if you look at your formula, I think you can see why. There's a fraction involved, and if that fraction was a 1, we'd have problems with that denominator, and it would be impossible to work out, solve, get an answer from. So knowing we have this geometric sequence, that we can then take the terms and add them together, and we would get a geometric series or sum out of it. We want to try that on a few problems, and that's basically this first part of section 11.5. So here's an example. Given the series, approximate s sub 8 to the nearest tenth. Now again, remember, this isn't just find the 8th term. It is the series of 8 terms, and you have to sum them or add them together. So you can see here we have our first term, our second term, our third term, our fourth term, and then etc. They didn't show you the other terms, and nor do we need to generate them based on what we just showed you in the formula. But you do want to make sure that this is a geometric, because that's what this sequence formula is for. So if you look at these here, most of you would say, oh, wait, 6 plus what? We're going in a negative direction. So you can see that we've got, to get back to 0, we're at 6, then we got to go another 14, so that's 20-something. And it's a negative 20. But then when we add a negative to a negative, so it's definitely not, because of this toggling between positive and negative, it is definitely not an addition sequence. So it can't be arithmetic, so therefore it is geometric, and your job is, hey, look and see what you have. We know we have a first term, second term, third term. So based on that geometric series, the formula said we needed our first term, which we have, that's 6. We needed also our constant rate. Well, we can't see our constant rate here, but we can definitely calculate it. So let's go. If we take that first term, 6, times it by some n value, we know we have to get to negative 14.4. So that's nothing more. If you just look at that, that's an easy way to set up your find that common ratio. And so we would divide both sides by 6. In doing so, we get an r value of negative 2.4. Once we have our first term and our r value, we can plug things right into that formula. So looking at it, there's the generic formula, s sub n equals, and now we're looking for the 8 terms in our sequence. So our first term was a 6. That's why we have that here. Our constant rate was a negative 2.4 that we used up here. So now we're going to substitute that in. The only caution is be very careful, because you need a negative number taken to a power. So that's why I'm using parentheses here. And then down below, it's 1 minus that rate. So make sure you're calculating the numerator and denominator separately. That would be a big difference. So when we do this one, we're getting an approximate negative 1,940.74-ish. And if they say round to the nearest tenth, then we're looking at a 0.7-ish. Watch directions because those rounding directions would be there. You should be able to, at this line, go right to your calculator, set it up, and let the calculator do the work. You shouldn't have to rely on your head or scratch paper to do that. Okay, next. What if we say and we apply it to a real-world situation? So, looking at this one, to save for a newborn child's college education, a family plans to invest $2,500 at the beginning of every year. So I'm just going to highlight as we go here to show things we definitely need. Okay, so that's $2,500 at the beginning of every year for 18 years. Now they're going to do that for how long? 18 years. Suppose the investment earns 6% annual interest rate, okay, and is compounded annually. How much will the investment be worth at the end of the 18th year? So now you have to remember there's two different time periods going on here. I believe they're investing the money at the beginning of each year, and then our question is asking for end. So that means at the end of the year, our sequence would look more like first term, second term, third term, and this would be at the end of year one. And then end of year two, end of year three, because we need to be making a sequence investment for the end of, 18 years. Okay, with that, let's now put in what we know and decide, again, what we don't know and start solving for it. So I think if we start thinking about this sequence, it's going to be that 2,500, but we have to do the investment. So if we do the investment on it, that's the number that's going to represent the end of the year, whereas the 2,500 by itself would have been the beginning of the year. So there's our first term, then our second term, and you can see it'd be a pattern of powers of 1.06 because it's compounded annually, so it means interest on interest, and we're good. So if you start looking at this and do the math, T sub 1 is that 2650 that we would calculate from above. We notice that we just have a new multiplier of 1.06 each year, and then we have that end value of 18. So we found, I believe, our needed values, because now that geometric sequence formula comes into play, and we will go for it. We need the first 18 terms added together, and that means we take that first term and multiply it by 1 minus r to the power of n. We're looking for 18, so that power should be an 18, divided by 1 minus 1.06. With that, doing the math, we'd come out with about $81,899.98. So we have, after 18 years, that child's college fund would be in the range of $81,899. That's a nice little chunk of change, considering you weren't planning on it to begin with. Okay. Questions? That would be how you would apply the same geometric series to a real-life situation. Then, don't forget that we've been working the whole entire chapter using summation notation. So in this case, we're looking at, a summation equation, and they want us to find the sum of the first 7 terms. How do I know that? I know my sigma stands for sum, and it's going from 1 to 7. Now, what I have to realize is, do I recognize this equation over here? And if I do not, then I have to generate some terms. And so if you do not recognize your equations, be very careful about what you're doing and generate some terms. So you could put a 1 in. 1 minus 1 is 0. Negative 5 to the 0 power is 1. 4 times 1 is 4. Start generating terms just like that. Then put a 2 in, then put a 3 in. But hopefully you're saying, well, that mirrors the equation we had that said t sub n equals t sub 1. So I'm looking at this as t sub 1, so that's the 4, times my constant rate r to the power of n minus 1. It looks like it mirrors exactly, and so 4 should be that first term. R should be that constant rate, and it is a negative. And so we could generate any other terms we needed. So here we go in our thinking. T sub 1 is 4. If we put another one in, t sub 2 to 2 minus 1 is 1. Negative 5 to the first is negative 5. Negative 5 times 4 is negative 20. R is that rate of negative 5. And now we can put it right into our summation equation. S sub 7, how many terms we're looking for, has to equal that first term, times 1 minus our rate, which is also a negative, to the power of 7 in this case. And then 1 minus a negative 5 on the bottom would turn into 1 plus 5. Continue doing that arithmetic, slowly and surely. You will get down to an answer of 52,084. So in this case, those 7 terms, even though you couldn't see any of them in that original problem, would be or would add up to be 52,084. All right, that is the first part of 11.5, where we're just dealing with geometric sequences and series summations, and so that's where we'll stop for the first part. If you have any questions, bring them to class.